Hi, Calculus 1 students. So this is the only optimization problem you have to look on YouTube. Um, you can certainly try this problem yourself. The reality is that we cannot teach all the possible optimization problem that there are in a calculus course. So a lot of them you'll have to figure them out by yourself. So you should certainly try this. It's actually an easy problem, not of the type that we have seen in class, but it's an easy problem that is certainly in your reach. So it's a geometric type of problem in the sense that you're trying to find a point on a given curve, let's say the parabola, which is over here, which has that formula. Okay, so that parabola here, let's remind that it has the formula 9 minus x squared. Okay, so this is a very good draw of it. Like the intercepts are -3 and 3. The vertex is right here at the y-intercept, which is 9. And we want to find which point on the parabola is closest to this point, the point 3, 9. So I tried to sketch it like as precisely as I can. It looks to be this point, okay? But to figure it out, let's have a look at how we set up the problem as an optimization problem. So I'm going to follow the same steps that we followed in class that are also in my lecture notes. So the step number 1 is actually the setup, the drawing, okay? So we define x, y to be a point on the parabola. And we want to minimize this distance d. Okay? So let's actually write this down. We want to minimize the distance d. Maybe it's not a good letter. Let's actually call this S. Okay. So this is actually step number 1. Step number 1, remember, it's the setup step. You draw, you assign variables. Okay. Step number 2 is to write down the objective function. So you want to have some kind of relationship involving the distance and the two variables you have. So step number 2, objective function. Okay. So you might remember that d. So actually, yes. Let's. Yes, actually, yeah, it's a good idea. Let's write d to be the square root. Okay. So this is the distance function that you have seen in high school. So this will be. Let's actually write its exact definition. Okay. So you have seen this before. Nothing new here. And we're having like x2 minus x1. And I will choose x2, y2 to be this point here. So like this is like x2 minus x1 squared plus y2 minus y1 squared. Okay, so this is the formula for the distance. And let's also replace x2, x1, y2, y1 by what they are. So in other words, what we have here is x minus 3 squared. 3 squared plus y minus 9 squared. Okay. Now, the step number 3 are to use the constraints. So, constraints. And here there's a single one. The constraint is that the point xy must lie on the parabola. Okay? And this means that xy satisfy the equation that's over here. So, satisfy this thing, right? So y is equal to 9 minus x squared. And this is very general in this type of problem. we are just saying that this has to be a point on the curve and not like everywhere else in the blank space. Okay, so it's on the curve. Okay. So now let's have a look at the best way we could possibly use this. Let's see. Yeah, as I can see, I don't see how much choice we have. We will actually replace the y directly by what this is. Okay, so here goes. We have d is equal to the square root of x minus 3 squared plus now we're gonna replace this y by 9 minus x squared, like this, and then obviously minus the 9, all of it squared. Rest stays as is. Okay. Now we're going to use an argument that sometimes you're going to be able to use, sometimes not. As you can see, the distance is always a positive number, something that is at least 0. And on that interval, the square root function is increasing. Okay, so let's actually write that. So the function, so f of x, that's equal square root of x, is increasing on the interval from 0 to infinity. So on 0 to infinity. Let's actually remove the 0, but because it's a boundary value. But the point is that it's increasing on this domain. So what does it mean? It means that instead of minimizing the distance, we can actually minimize what's inside the square root. Okay? So instead of minimizing d, we can minimize its inside. Okay, so how do we do this? Well, we're gonna just define another function. So let's call it. We're gonna call it capital D, or actually, yeah. Remember we said that S is gonna be our distance. So here I kind of messed up. So S, S, and S. So let's call it capital S. Okay, so capital S of x will be just the inside. Okay, so x minus 3 squared. And now the 9's will cancel, the negative will get squared. So we will get here plus x to the power of 4. Okay. All right. Now that we have this function of only one variable, we can erase everything here. Let's do it. The step number 4 is to determine in which interval we are minimizing. Okay, so number 4, interval. Okay, so I unfortunately erased the drawing. One thing that we could do is we could actually minimize on the interval from 0 to infinity, because it's obvious by the symmetry of the problem that the negative part of the parabola will not, like the point won't be on the negative part of the parabola. But let's suppose that we don't know that, and worst case scenario, we're going to use it later on. So let's say that, okay, so x can be any real number, so which means that the interval is from negative infinity to infinity, which is a bad news. It means that we cannot use the closed interval method. So no closed interval method. Okay. Now step number 5 is to actually take the derivative of our objective function. Okay, so capital S prime of S. So this is the easy part. We're going to use the chain rule on this. So twice x minus 3 to the power of 1, obviously, but let's write it down just to be really, really clear. Times 1, okay, well, chain rule. And then we're taking the derivative of this guy, which is 4x to the power of 3. Okay? All right. And now let's see what we get from here. So we get twice the x, so 2x. Then we're going to have minus 6 plus 4x to the power of 3. All right. And from there, we need to find the critical values. So as I can see, we have a problem here in the sense that we have like this equation that I'm not sure if we can find the solutions of easily. So let's call this step number 6, critical values. Okay, so all right. So obviously there is no value for which s prime of x is equal to dne. Okay, so this happens nowhere. And now, are there values for which s prime of x is equal to 0? Now, I'm a little bit scared because this is a cubic, so I don't see like any kind of way to solve it in general. But let's try, okay? Let's actually set 0 is equal to this. Okay, then plus 2x minus 6. Okay, and then let's take out the 2. So we're going to have like 2x cubed plus x minus 3. And one thing that we can notice, actually, this is going to save us, is that x equals 1 is a solution. Okay, so x equals 1 is a critical value. So makes 2x cubed plus x minus 3 equal to 0. And this means that x minus 1 is a factor of 2x cubed plus x minus 3. Now, to find the other factor, we need to perform long division. So let's see if we actually get another solution. So to find the other factor, use long division. So you know how to do this. Okay, so you put like 2x cubed plus, let's put the 0x squared plus x minus 3. And now let's put the x minus 1. This should be fairly quick. So we're going to have 2x squared. So meaning we have like the 2x cubed minus 2x squared, subtract. So we have 2x squared plus x minus 3. Now let's push on with the division. So this is going to give us 2x squared divided by x will give us 2x. So we have 2x squared minus 2x. That's it. So we have finally 3x minus 3. And finally, this divided by this is going to give us positive 3. So then we're going to have finally 3. Yeah, x times 3 is going to be 3x. and that's it. 1 times 3 is -3. So then we subtract and we get 0. Okay, which is expected. So the idea was to find the other factor, the one that's right here. Okay, so let's replace. So we have here that, all right, so 0 is equal to x minus 1 times 2. Okay, so I forgot the 2 here. So we're going to have 2 times x minus 1 times, and now we punch in this factor. So 2x cubed plus x minus 3. Is that it? No, plus 3. There we are. And it's fairly easy to see that this is not factorable. Okay, so this is not factorable. Okay, so the idea is to compute the discriminant, which you know very well, minus b squared plus 4, no, b squared minus 4ac. As I can see, you know it better than I. So it's going to give us 1 minus 4 times 2 times 3. So in other words, this is like, so it's going to give -23, so smaller than 0. Okay, so this means that x equals 1 is the only critical value. And this is an amazing news because it opens up the setup for the second derivative test or the first derivative test using with absolute extrema. Okay, and this is the step number 7. Okay, so step number 7 is to do the test. And here we are. We got this function. This is our derivative. Okay. So s prime was equal to this thing. So 4x cubed plus 2x minus 6. And now we're going to perform the second derivative test. So s prime prime of x, which is going to be 12x squared plus 2. And as you can see, regardless of s, it is positive. But just to get a complete setup, so s prime prime of 1 is going to be 14, so that's positive, which means that this critical value gives rise to a relative minimum, which then turns out to be the absolute minimum because it's the only relative minimum. So, all right, let's erase this. And actually, let's erase everything. So S has a relative min at x equals 1, which is the absolute min. Since it's the only critical value. And from there you can conclude, right? Because you have the x coordinate of the point and you know how to find the y coordinate. Okay, so you know that x is equal to 1, y is equal to 9 minus 1 squared, which is equal to 8. So as a conclusion, the point 1, 8 is the closest point to the point that was given, right? 3, 9. That is on the parabola. All right. I'm sorry for the long video. It took longer than expected. It was mainly because of the use of the factor theorem, as you can see. So I'm not really expecting you to know the factor theorem for the exam. It was actually not expected. Like I didn't know I was about to use the factor theorem in this example. But it's just keep in mind the procedure is the same anyways, right? You're just finding the critical values by whatever mean is available, and you might have to solve different types of equation in order to get there. All right, I hope this helped. See you either in class or in the next video.